This is just going to be a quick video covering section 6 of chapter 1 in your textbook, and it's going to talk about formulas and models. While this is a very short section, it is important that you get down the vocabulary associated with this section because these are words we're going to use time and time again as we go through this course. The first of these vocabulary words is that of a molecule. And a molecule is a collection of atoms that chemical bonds hold together in a particular pattern and proportion. So these molecules can either be composed of a lot of different atoms, sometimes more than one of the same atom combined with a lot of different other things, or they can be the same atom kind of linked together. So we see two of those examples down here. So on the left side, we see this little black sphere along with these two little red spheres. We've got a whole bunch of molecules of that. So this is your book's representation of carbon dioxide, which is the black sphere, and two oxygens, which are the red spheres. So each molecule of carbon dioxide will have one carbon and two oxygens, no matter where you find it in the world, whether it's being, exhaled by you or your friend or just around in the atmosphere. It's going to have one atom of carbon, two atoms of oxygen. And your book is actually really nice because it uses the same colors for the particular atoms all throughout the book. So carbon will always be a black sphere, oxygen will always be a red sphere. On the other side, on the right-hand side, we see sets of two atoms that are bonded together. And we see red spheres, which we know from over here, red is oxygen. So this is oxygen gas. The yellow spheres are kind of small. Those are hydrogen gas. And the blue spheres are nitrogen. So that's nitrogen gas. So these guys are an example of a diatomic molecule because it has two atoms, diatomic, two atoms, of the same molecule. So when you find hydrogen in nature, it's always going to come with its buddy. So it's always going to be H2, so two atoms of hydrogen. Oxygen gas is always going to be O2, and nitrogen gas is always going to be N2. Now, that's not to say that hydrogen, oxygen, and nitrogen can't bond with other things, but if they come like pure to you, they're always going to be diatomic. So H2, O2, N2. And then your book talks about what we'll learn to know as the halogens, so fluorine, chlorine, bromine, iodine. Those guys are all diatomic as well. Here we have a peek into all the different ways that these molecules can be represented. So we're going to start up the very top with the molecular formulas. So these molecular formulas just show you what particular atoms are in that molecule, and then how many of each is represented by the subscript. So here we're looking at, this is acetone, so it has 3 carbons, 6 hydrogens, and 1 oxygen. Now this doesn't tell you anything about how it's bonded together, who's next to who. This just tells you what atoms and how many of each there are. Over here we've got acetic acid, which is the primary component in vinegar. It has 2 carbons, 4 hydrogens, and 2 oxygens. Moving down, we have our structural formulas. So this shows you, again, we've got for acetone, we have our 1, 2, 3 carbons. We have our 1, 2, 3, 4, 5, 6 hydrogens, and our 1 oxygen. All right? But this shows us kind of how they're bonded together. So this represents that this carbon is bonded to an H, another H, another H, and a carbon. This carbon's bonded to 2 C's, and it's got a double bond here, so 2 bonds to oxygen. And then this carbon is just like the left-hand carbon where it's bonded to 3 H's and a C. We see over here with the acetic acid, again, we've got a carbon bonded to 3 H's and a carbon. Again, we've got a carbon with 2 bonds to O, 1 bond to this O and 1 bond to this carbon. And this oxygen has a bond to an H and a bond to a carbon. So this shows you kind of what the structure kind of looks like when you draw it out. Then we move on to our condensed structural formula, which is similar to the structural formula. But we see here where we've got this carbon bonded to 3 H's. Instead of drawing all of those out, it just kind of throws them in one line. So we have H3C, meaning that this carbon is bonded to 3 H's. And then we show the bond to the other carbon. Same on this side. The next one is the ball and stick model, where again it uses those spheres, black for carbon, red for oxygen, white for hydrogen. So this shows, again, not only how it's bonded, but it starts to kind of represent it in three-dimensional space. Because remember, just because you can draw it flat doesn't mean it's a flat molecule. These are actually, three-dimensional molecules, so they have some dimension to them. So here, again, we see this carbon's again bonded to 1, 2, 3 H's and another carbon, so it's all bonded the same way. But we can kind of see that these two bonds are kind of in the plane of the paper. This guy's going away from you, kind of into the screen. This guy's popping out away from the screen. So we're starting to see some dimensionality to these carbon atoms. You can see that over here as well. And then it also kind of starts to give you an idea of relative sizes. You can also start to form an idea about relative bond angles. So we see this little bond angle here is a little bit smaller than this guy here. So while you can see angles and you can see kind of relative sizes and you can see dimensionality, it kind of gives the impression that these atoms are far apart when in fact they actually overlap with each other. So enter the space filling model. So you can kind of see these are kind of big fluffy atoms, and you can see how they overlap with each other. You can still get an idea that it's still a three-dimensional object. It's not quite as apparent in this one as it is in this one, but it just kind of gives you an idea of kind of how fluffy the molecule is. But again, using this model, determining bond angles and that sort of thing is quite challenging. So we're going to use a combination of all 5 of these different models. Now, not all compounds show up in molecules. Sometimes compounds have positively and negatively charged ions, and that kind of electrostatic attraction of the plus to the minus is what holds them together instead of these chemical bonds. So these guys are called ionic compounds. So here we have a picture of table salt, obviously a really zoomed in picture, and this is kind of what table salt would look like real close up. So you've got sodium plus cations that are attracted to the chloride minus anions, and this plus minus is what keeps them attracted together. So these guys kind of show up in a three-dimensional array, so you see it kind of goes back, so plus minus plus minus, plus minus plus minus, up down, sideways, all the way around. So this is a three-dimensional array that we refer to as a crystal. These guys are reported as the simplest whole number ratios of plus charges to minus charges. So since we don't have a discrete molecule like we did with, say, acetone and acetic acid, we're not going to sit here and count how many Na pluses and Cl minuses you have. So you're just going to take the simplest whole number ratio. So this is referred to the empirical formula. So the empirical formula of sodium chloride is NaCl, meaning that for every 1 sodium cation, you have 1 chloride anion. This empirical formula can also apply to molecules as well. So we can also calculate the empirical formula of our molecular formulas as well, so of our molecules. So here we have acetone, so we have C3H6O. So if you were to reduce this down to its simplest whole number ratio, so you're going to divide all of the subscripts by what they have in common, you're still going to get the same formula because you've got a 3, a 6, and a 1. So you divide everybody 1 by 1, you get the same number. If we look at acetic acid, which has the formula of C2H4O2, we can see that if we divide each of these numbers by 2, we can bring this down to our simplest whole number ratio. So it would be CH2O. So this would be our empirical formula of acetic acid, and it obviously doesn't tell us the whole story, right? So we don't quite know how many C's, H's, and O's there are in this guy. We know that the actual molecular formula is going to be some multiple of this. So to go from the molecular formula here to the empirical formula is pretty easy, but to go the other way, you're going to need more information because, this could be So here we times it by 2, it could be times 3, it could be times 4. So we would need more information to go from empirical to molecular. But again, that's a story for another day. All right, so that's all for this section. So again, remember these definitions. They are going to come back again and again and again throughout this entire course. And as always, don't hesitate to reach out if you have any questions about anything I cover in any of these videos. Thanks, guys.